Next story. Unraveling the science of fear in the brain. In a groundbreaking study led by neurobiologists at the University of California, San Diego, the mystery behind how stress-induced generalized fear unfolds in our brains has been unraveled. Published in the prestigious journal Science, the research sheds light on the intricate changes in brain biochemistry and neural circuitry that underlie the experience of pervasive fear, such as that seen in conditions like PTSD. The team, including former UC San Diego assistant project scientist Hui-Quan Lee and Professor Nick Spitzer, pinpointed a pivotal switch in neurotransmitters within the dorsal raphe of the brainstem. This switch, from excitatory glutamate to inhibitory GABA neurotransmitters, was found to trigger generalized fear responses in the absence of real threats. By delving into post-mortem human brains of PTSD patients, the researchers confirmed this neurotransmitter switch, providing crucial insights into the mechanisms driving fear generalization. However, the study didn't stop there. It proposed innovative methods to halt the production of generalized fear. Through the injection of an adeno-associated virus to suppress GABA synthesis in mice prior to acute stress exposure, the onset of generalized fear was prevented. Additionally, administering the antidepressant fluoxetine immediately after stress prevented the transmitter switch, offering a beacon of hope for those vulnerable to fear-induced conditions. Not only did this research identify the precise neurons and neural connections involved in stress-induced fear responses, but it opened the door to targeted interventions. By understanding the core mechanisms behind fear generalization, such interventions can be tailored to specific neural circuits, paving the way for more effective treatments. This study not only deepens our understanding of how fear manifests in the absence of real danger but also highlights the potential for groundbreaking interventions in conditions linked to fear and trauma. The implications of this research are profound, offering new avenues for treating debilitating mental health disorders and providing hope for those grappling with the shadows of fear within their minds. Source: Uric Alert. Next story. Rising bacterial infections. Breakthrough blood test at Tulane University reduces diagnosis time from months to hours. In a world where infections from non-tuberculosis mycobacteria are on the rise, Tulane University researchers have unveiled a groundbreaking blood test that slashes diagnosis time from months to mere hours. Gone are the days of uncertainty and waiting. This innovative platform can now provide results within 2 hours, a vast improvement from the previous 6-month slog. Non-tuberculous mycobacteria, commonly found in water, soil, and dust, may be harmless to many but pose a serious threat to those with underlying conditions. These bacteria can infect the lungs, leading to symptoms akin to tuberculosis. The slow growth of NTM has historically made diagnosis and treatment a lengthy ordeal, but not anymore. The blood test, based on CRISPR technology, boasts an impressive accuracy rate of over 93% in identifying NTM infections. As cases of NTM infections surge annually, exacerbated by global climate change, rapid and precise diagnosis has become more critical than ever before. Dr. Bo Ning, the lead researcher and assistant professor at Tulane University School of Medicine, highlighted the importance of this breakthrough. He emphasized the test's ability to swiftly detect Mycobacteria avium complex, MAC, a prevalent type of NTM responsible for pulmonary diseases. By detecting NTM DNA fragments in the bloodstream, the test circumvents the need for prolonged bacterial cultures, streamlining the diagnostic process significantly. The implications of this advancement extend beyond mere convenience. With the ability to infer drug responses, this blood test empowers healthcare providers to swiftly determine treatment plans, a feat unattainable through traditional methods. Dr. Ning envisions a future where this test becomes a staple in clinics worldwide, revolutionizing the landscape of NTM diagnosis. As the specter of rising NTM infections looms, accessible and efficient testing methods are crucial to curbing potential outbreaks. Collaboration with Oregon Health and Science University has further bolstered the study's credibility and impact. The journey doesn't end here. Dr. Ning aims to broaden the scope of NTM types detectable by CRISPR technology and develop point-of-care tests for seamless NTM detection. By reducing barriers to testing and diagnosis, he aspires to fortify our defenses against the looming threat of NTM infections. This scientific feat, documented in the American Journal of Respiratory and Critical Care Medicine, signals a new dawn in the battle against NTM infections. With this innovation at our disposal, we stand better equipped to confront the challenges posed by these escalating infections and safeguard public health. Source: Uric Alert. Next story. Mapping unburnable oil reserves worldwide. Research from the University of Barcelona. In a groundbreaking study led by the University of Barcelona, a new chapter in the fight against climate change has emerged. The research, published in Nature Communications, unveils an Atlas of Unburnable Oil, a global map designed to pinpoint oil resources that should remain untapped to honor the commitments of the Paris Agreement. Professor Martí Orta Martínez, along with an international team of researchers, sheds light on the critical need to steer clear of exploiting oil reserves in areas of paramount socio-environmental importance. These regions include natural protected areas, crucial biodiversity hotspots, urban centers, and territories inhabited by indigenous communities in voluntary isolation. With the objective of limiting global warming to 1.5 degrees Celsius, the study emphasizes that refraining from extracting oil in these sensitive zones is imperative but insufficient in itself to meet the Paris Agreement's targets. The researchers emphasize the necessity of halting the exploration and extraction of new fossil fuel reserves and advocating for the premature closure of a significant proportion of existing oil, gas, and coal projects. The Atlas serves as a comprehensive roadmap aligning with international climate policies, steering the energy sector towards sustainable practices. It calls for a paradigm shift towards clean energy investments, urging governments, corporations, citizens, and investors to divest from the fossil fuel industry and accelerate the transition to renewable energy sources. The study's findings underscore a stark reality: the window to limit global warming is rapidly closing. If current emission rates persist, the remaining carbon budget for a 1.5 degrees Celsius target will be exhausted by 2028. The combustion of known fossil fuel reserves would unleash a catastrophic 10,000 GT CO2, far exceeding the limits set by the Paris Agreement. As the scientific community advocates for urgent action, the researchers urge a collective effort to avert irreversible climate change impacts. Governments and stakeholders are implored to prioritize sustainability, enforcing stringent measures to curb emissions and safeguard the future of our planet. In a race against time, the call for immediate action reverberates loud and clear. The Atlas of Unburnable Oil serves as a beacon of hope, illuminating a path towards a sustainable and resilient future. It beckons us to rise to the challenge, to embrace clean energy solutions, and to forge a world where environmental preservation stands at the forefront of our endeavors. The fate of our planet hangs in the balance. The time for change is now. Source: Uric Alert. Next story. Unveiling the boundaries of electromagnetic energy absorption. In a groundbreaking revelation that has eluded scientists for over 2 decades, researchers at Duke University have unlocked the theoretical limit for how much electromagnetic energy a transparent material of a specific thickness can absorb. This discovery, published in the journal Nanophotonics, is set to revolutionize the design of devices that block certain radiation frequencies while permitting others to pass through, notably for applications like stealth technology and wireless communications. Led by Professor Willy Padilla and his team, this study has cracked a mathematical conundrum that had stumped researchers for years. Unlike the previous solution crafted by Rozanov, which involved a metal-lined boundary to simplify the calculations, Padilla's team tackled the challenge without this convenient edge, thereby delving into uncharted territory on the electromagnetic spectrum. Through a collaborative effort that harnessed the expertise of Professor Vahid Tariq and research assistant Yang Deng, a novel mathematical approach was devised, offering a fresh perspective on the problem. Tariq's ingenuity in reshaping the conundrum led to a breakthrough, demystifying the elusive fundamental limit of absorption bandwidth relative to material thickness. Not only does this research mark a triumph in unveiling a long-sought-after answer, but it also holds profound practical implications across various domains. By understanding the fundamental limits of electromagnetic absorption, engineers can tailor devices to selectively block or permit specific frequencies, a crucial capability in scenarios such as mobile communications where certain radiation types must be attenuated while others remain unimpeded. This newfound knowledge not only empowers designers to optimize the efficiency of the devices but also guides them on when further refinement may yield diminishing returns. For instance, in the realm of cellular technology, being able to discern the absorption limits of different frequencies enables engineers to craft systems that safeguard against harmful radiation while facilitating the passage of essential signals like GPS or Bluetooth. Supported by the Department of Energy, this research embodies the spirit of innovation and interdisciplinary collaboration, shedding light on a fundamental aspect of electromagnetic energy absorption that has eluded researchers for far too long. As the scientific community absorbs the implications of this breakthrough, the possibilities for future advancements in technology and engineering appear boundless. Source: Eureka Alert. Next story. Analog computing. Efficient equation solving with minimal energy. Study from University of Massachusetts Amherst. In a groundbreaking study led by researchers from the University of Massachusetts Amherst, a revolutionary analog computing device known as a memristor has demonstrated its ability to solve complex scientific problems while consuming significantly less energy than traditional digital computing methods. Digital computing has long faced challenges in processing large-scale scientific equations efficiently due to the constant need to transfer data between memory and computing units, leading to energy consumption bottlenecks and processing delays. The team, including UMass Amherst professor Changfei Chia, has introduced an innovative solution using memristor technology, which combines memory and resistor functions in a single device. By implementing in-memory computing with memristors, the research team has overcome the limitations of traditional computing by reducing data transfers and processing information directly on the device itself. This approach not only boosts computing speed but also minimizes energy consumption, akin to streamlining traffic flow on a nearly empty road during a pandemic. The memristive circuit, when organized into a crossbar array, enables analog computing in a massively parallel fashion, accelerating matrix operations and enhancing information density within a single cell. This breakthrough opens up new possibilities for a wide range of applications, from machine learning to high-precision scientific computing tasks previously considered challenging for digital systems. The study marks a significant leap forward in analog computing technology, showcasing the memristor's ability to solve static and time-evolving partial differential equations, Navier-Stokes equations, and magneto-hydrodynamics problems with exceptional precision and efficiency. The researchers' dedication over a decade has yielded tangible results, paving the way for the integration of memristors into semiconductor industry practices and benefiting the broader AI hardware community. The potential of memristors extends beyond traditional computing boundaries, offering a promising alternative for enhancing both low-precision neural network operations and high-precision scientific calculations. The research not only pushes the boundaries of analog computing but also highlights the versatility and efficiency of memristor technology in addressing complex computational challenges across various fields. As the scientific community embraces this paradigm-shifting technology, the future of computing holds immense promise, with memristors poised to revolutionize the landscape of AI hardware and scientific computing applications. Source: Eureka Alert. Next story. Uncovering unique brain structure in children with language development issues. In a groundbreaking discovery, Georgetown University Medical Center neuroscientists have pinpointed an abnormality in the brains of children with developmental language impairments. This finding, published in Nature Human Behavior, sheds light on a previously unrecognized disorder that affects language development in children. The researchers focused on the anterior neostriatum within the basal ganglia, a region of the brain traditionally associated with movement. Through a comprehensive analysis of 22 studies, they observed abnormalities in this specific brain structure in 100% of cases involving developmental language disorder, highlighting its significance in language difficulties. Lead author Michael T. Ullman, Ph.D., emphasized the importance of understanding the neural basis of developmental language problems to raise awareness and improve diagnostics and treatments. The study suggests that drugs targeting dopamine receptors, known to improve movement impairments related to basal ganglia dysfunction, could be beneficial. Additionally, interventions focusing on intact brain structures and utilizing basal ganglia abnormalities as early biomarkers may lead to early therapeutic interventions for affected children. The potential implications of this research extend beyond diagnosis and treatment. By unraveling the neurobiological underpinnings of developmental language disorder, especially the role of the basal ganglia, researchers aim to provide much-needed support to the numerous children grappling with these challenges. The study was a collaborative effort involving researchers at Georgetown University, Deakin University in Australia, and the University of Minnesota Medical Center. Financial support from various sources, including NIH and NSF grants, enabled this critical research to advance our understanding of developmental language impairments. Georgetown University Medical Center, known for its commitment to education, research, and patient care, continues to push the boundaries of scientific discovery. Through interdisciplinary collaboration and a dedication to improving human health, GUMC exemplifies the ethos of cura personalis, caring for the whole person. As we delve deeper into the complexities of the human brain and its impact on language development, this study serves as a beacon of hope for children with developmental language impairments and their families. By uncovering the neural mechanisms at play, we move closer to personalized interventions and improved outcomes for those affected by this often overlooked disorder. Source: Euric Alert.